PDE. So I'll say just a few words. This workshop was supposed to happen in 2020, but because of the pandemic, we had to reschedule, and we thought this year we would be able to do this workshop in person, but unfortunately it was not possible, and we decided to transform this workshop in an online workshop. But we are very happy with the result. We had a lot of great talks, very great program, and I hope you all enjoy it. And it's a great pleasure to me to introduce the first speaker and start with Helena. So okay, we are live on YouTube. So Helena Nussenzveig Lopes is the first speaker of this workshop, and she's going to talk about 2D NeverStokes in bounded domains with holes in Navier boundary conditions, and she's from Universidade Federal do Rio de Janeiro. Thank you very much.
Okay, thank you, Annie, for the introduction, and it's a great pleasure to see all of all the friends together here, even if only virtually, and also to be part of this workshop on fluids and PDE, which was actually a very long time in the making. Annie said that this was supposed to happen in 2020, but actually this was planned for much earlier, and we just kept on postponing. It was supposed to be held in 2017, and then 2018, 2019, 2020. Well, here we are, 2021. Okay, so I'm going to be talking about 2D Navier-Stokes equations in bounded domains with holes and the Navier boundary conditions. Oops, okay, here we go. So let me start by introducing my collaborators in this joint work. This is based on joint work with Christophe Lacave from the Université de Grenoble, Milton Lopes Filho from Universidade Federal do Rio de Janeiro, UFRJ, and Jim Kelleher from the University of California, Riverside. Okay, so let me start with a small introduction. This is 2D. And so I'm going to take omega, a bounded, smooth, connected domain. And when I take smooth, just think of something with a C infinity boundary. Okay, not necessarily simply connected with holes, in other words. So the 2D Navier-Stokes equations with Navier friction boundary conditions on the domain omega are given by the following system. So you have the Navier-Stokes equations, dt u plus u grad u is minus gradient of pressure plus nu Laplacian u. The divergence-free condition, we have the initial value, u at time t equals 0 is given. It's the initial velocity. And the boundary conditions are non-penetration, u dot n equals 0, and twice sun dot tau plus alpha u dot tau equals 0 on the boundary. Okay, so we will refer to this as 2DNS with NBC. So what is SUN? SU is just the symmetric gradient. So it's the stress tensor matrix. Okay, so twice SU is the Jacobian matrix of U plus its transpose. Okay, alpha is the Navier friction condition. Okay, so Navier friction coefficient. I'm sorry. And we're going to assume it's not constant. So it depends on where you are at the boundary. And it's smooth and time independent. It's given. It's a given. Okay. So this boundary condition is known as a Navier friction condition. And SUN is the stress across the surface, across the boundary. And SUN dot tau is, or twice SUN dot tau is the tangential stress across the boundary. Minus alpha u dot tau is the resistance due to friction. And here we're thinking of the physically correct model where alpha is positive. The friction coefficient is positive. So this condition was introduced originally by Navier himself in 1827, and it was later derived by Maxwell in 1879 from the kinetic theory of gases by an averaging process. So the condition, sorry, this is supposed to be U dot N, not U dot nu, together with the Navier friction condition, which is also known as slip with resistance, are known as the Navier friction conditions. And they've been used in the modeling of turbulent geophysical flows, 2D turbulent geophysical flows. And there's a paper by John Layton and Sahin from 2004, where they discuss the numerics associated to this model. Okay, so LES, et cetera. And it has been analytically rigorously justified as a homogenization of no slip on rough boundaries. And this is some work by Willy Jager and Andra Mikulic from 2001, 2003. And for those of you who don't know, Mikulic passed away last year. It was very sad. Okay, so what we want here is to understand the large time behavior of the velocity field U and the vorticity, which in 2D is identified with the scalar grad perp dotted with U. That's not supposed to be grad perp of U, that's supposed to be grad perp dotted with U. So there's a typo there. Okay, now, being as we are mathematicians, we're going to broaden the scope of the problem and relax the condition on the friction coefficient alpha. So we will no longer require that alpha is positive. So alpha positive is the physical condition, assuming that this is a physically reasonable model, which in some scenarios it is. Okay. And but we're not going to assume that. Okay, so instead, let kappa of x be the curvature at different boundary points, and we will assume one of the following conditions. Either alpha is non-negative, okay, if the domain is simply connected, if it is not a disk, okay, and if the curvature is non-negative everywhere. In other words, if you have a simply connected convex domain, which is not a disk, then we will have to assume alpha is non-negative. If the domain is simply connected, not a disk, but the curvature change is sign, such as for a little potato or an amoeba, then we have to assume that alpha is greater than or equal to twice the curvature at each point. Okay, we do not have the option of assuming one condition on one portion of the boundary and another condition on the other portion of the boundary. So if the curvature changes sign anywhere on the boundary, then we have to assume that alpha is greater than or equal to twice the curvature. And if omega has holes, or if it is a disk, then we will assume that the coefficient is greater than or equal to the curvature. So these are kind of like the weakest conditions that you can assume on the friction coefficient alpha in order to make everything work. Okay. So our main result in this work is the following theorem. If we assume either condition 1 or 2 or 3, and if the initial velocity U belongs to H2, the Sobolev space H2 is divergence-free and tangent to the boundary, and satisfies the Navier friction condition on the boundary, then if you have a strong solution to NeverStokes to 2D NeverStokes with Navier boundary conditions, and if omega is the curl of U, then both U and omega decay exponentially in time, in both L2 and L infinity. So this is not really a surprising result, okay, not at all. This is sort of expected, but there are some intriguing features to it. First of all, the methodology is kind of interesting, and the fact that the annulus and the disk play a distinguished role in the analysis is kind of intriguing. Okay, so more specifically, we have the following estimates. The L2 norm of the velocity at time t is bounded by the initial L2 norm. I'm sorry, the L2 norm of the initial velocity times the exponential for some constant, positive constant c, minus c nu t. The L infinity norm is bounded by a constant d times this negative exponential. The L2 norm is bounded by k times 1 plus d. And the L infinity norm is also bounded by k times 1 plus d. Now, d is proportional to twice the curvature minus the friction coefficient, L infinity norm. And K is just a constant, which depends on the initial data and the domain. Okay, so it's interesting here just to notice that the friction coefficient does not appear at all in the exponent for the exponential, for the negative exponentials, but it does appear as a coefficient for the L2 and L infinity norms of L infinity norms of U and omega and the L2 norm of omega. Okay, in other words, the greater the friction or the greater the curvature, the more decay you have, but only as a coefficient. This is to linear order. Okay, it is possible to, make more precise these constants C, and actually they're different for different scenarios for cases 1, 2, or 3. But for the purposes of this talk, I think we can put, just take the minimum of them. Okay. Okay, so let me give you some motivation for why we looked at this problem. What we were truly interested in was, suppose that you have a domain with M holes, okay, and let a gamma M plus 1 denote the outer boundary of this domain. Then from the fact that U is divergence-free and tangent to the boundary, you can conclude that U is going to be K of omega plus H, where H is a harmonic part. So if you have a hole, you have a harmonic part. This is the Hodge-Durham theorem. And K of omega is going to be the Biot-Savart kernel, Biot-Savart law. So H there are known as harmonic vector fields. You have M of them, and they generate all of the vector space of harmonic vector fields. Harmonic vector fields are curl-free, div-free, tangent to the boundary. And K of omega is just the grad perp of the Laplacian inverse of omega with Dirichlet conditions for the Laplacian inverse. Furthermore, we can determine exactly who are the coefficients of the harmonic part Hj. So Hj is just a basis. It's a basis for my vector space of harmonic vector fields. Now, these Aj's can be determined once we specify which Hj's we're talking about. And for a specific set of harmonic vector field basis, Aj is given by the circulation around each hole plus the integral of vorticity times phi j, where phi j are known as harmonic measures. They're functions that are harmonic in the interior of the domain, and on each boundary, they're given by the Kronecker delta. Okay, so on the boundary of each of each hole, gamma k, for k from 1 all the way up to the outer boundary, you have phi j is delta jk, but j only goes from 1 to m. J goes from 1 to m, so there is no phi m plus 1. Okay, now, as early as 1998, Cihiclopo, Andrei Mikulich, and Hauhober looked at this problem, and they were interested in the vanishing viscosity limit, the inviscid limit with never boundary conditions, which, albeit not a physically correct problem, it's still mathematically interesting, and actually you can pass to the limit. We'll see later why exactly you can pass to the limit when viscosity vanishes. And they proved first for vorticities in L infinity, and then Milton and I, together with Gabriela Planas in 2005, extended this to vorticities in LP for any p larger than 2, and this was all done in a simply connected domain. And then Jim Kelleher, in his thesis in 2006, extended this to the case of domains with holes, multiply connected domains. So we all proved that the vanishing viscosity limit of 2D NeverStokes with never boundary conditions corresponds to the Euler equations, to a solution of the 2D Euler equations in the same domain with the same initial data. Okay, so this is a finite time horizon result. And what we were really interested in is that since for the Euler equations, the circulations along the boundary components are conserved, we wanted to understand what was, and we do understand the evolution of the integral of omega times the harmonic measures for Euler solutions. We wanted to understand what would be the behavior of these circulations with respect to viscosity as viscosity became very small, and of these coefficients A, J, nu of T. Okay. And this is still work in progress. We still have not understood this, but this was the motivation. We started to look at this problem, and then we started to do some calculations with some steady solutions, and finally we realized that not even the large time behavior was understood. So that's how we got into this problem. Okay. Eventually, what we would like is to do a shrinking of one of these holes, and understand what happens when the diameter of the holes vanishes, and whether you converge to Euler or whether you have a Dirac at the hole, etc. Okay, so this is related to other work that we've done in the past with no slip. Okay, so the first thing that we had to do was to actually establish well-posedness, and in what sense, for the NeverStokes, 2D NeverStokes equations in a domain with holes and Navier boundary conditions. And although Jim Kelleher did cover this in his thesis paper, we thought that there were some issues that needed more careful look. And so we went back to this. And so what I'm going to tell you now is mostly in Jim's thesis, but not all of it. Okay. So first we introduced a basic function space. As H is L2 divergence-free tangent to the boundary. It's the same as always. X is going to be H intersect H1. So it's H1 vector fields that are divergence-free and tangent to the boundary. And this is in the NeverStokes literature, typically this is known as V, except that that's going to be H intersect H1, 0. So in this case, we do not assume H1, 0 because we're not doing no slip. And W is a space which is adapted to the Navier boundary conditions. So it's H2 vector fields, 2 derivatives in L2, divergence-free, tangent to the boundary, and such that these Navier friction conditions hold on the boundary. Okay, so note that in order to write these conditions, you need a trace of SU in particular, and SU involves a derivative, so you need to have something in H2. You need more regularity in it in order to be able to talk about the trace of a derivative. Okay, we will also introduce the abstract dual space, which we'll need X prime. Okay, so what we want is a strong solution with initial data in W. Okay. And to do this, we follow the standard strategy, existence and uniqueness of some kind of weak solution for initial data in H. Then we follow up with showing a higher regularity if the initial data is in a better space, is in a W. And the crucial issue is, in order to talk about weak solutions, is how do you incorporate the Navier boundary conditions in a weak formulation? Okay, because as I said, you kind of need the trace of SU, of a derivative. Okay, so the first observation that we make, this is basically Jim's doing, is that if U is in W and V is in X, in other words, if U is H2 and satisfies the Navier boundary conditions, and V is only H1 and is tangent to the boundary, then if you look at the Stokes operator on H2 minus the Leray projector times the Laplacian, then you find the following, integration by parts, you find the following set of identities. The integral of AU dot V which is minus the integral of the Laplacian of U dot V because the graded term vanishes. And then you integrate by parts and you get du double dot the trace product with dv plus the integral on the boundary of dun dot v. Okay, so du is the Jacobian matrix of U. And for this, here's where I need to have a trace of du on the boundary. So this is where I need U to be in W, H2. Okay. So this can be rewritten in one of the following ways. The integral inside the domain, using the fact that U satisfies the Navier boundary conditions, this is the integral inside of the domain of the trace product of the gradients plus the integral on the boundary of alpha minus kappa, and here's kappa appearing for the first time, times U dot V. Okay. Notice that this term here, all you need is H1 for this term, because all you're taking is the trace of U on the boundary. This can also be rewritten as twice the stress matrix SU, the stress tensor SU, trace product with SV, plus alpha times U dot V, and here there's no kappa appearing, or the integral of the curl of U times curl of V, plus the integral on the boundary of alpha minus 2 kappa U dot V. Okay, so each of these three expressions makes sense if only U and V are H1, because all you need to do is to take traces on the boundary of U and V. And for a fixed u and x, this gives rise to a bounded linear operator on x. In other words, an element of x prime. Okay. Now w is dense in x. Okay, so this was established by Klopot, Mikulich, and Robert in 1998 in the case of simply connected domains, and then extended to multiply connected domains by Jim in his thesis. Okay, so therefore you can extend this Stokes operator from w to x in a unique way. And it gives rise to an operator which takes x into its dual. Okay, so by density, you have a unique extension. And so any of these three expressions may be used interchangeably. Okay, so here's a definition of weak solution that we're going to be using. Take initial data in H. Then if U is a function which is continuous into H and L2 into X, remember X has more regularity, it's H1, such that the partial time derivative of U is L2 into X prime, the dual space. This will be a weak solution of the 2D NeverStokes equations with never boundary conditions with initial data U naught if the following identity holds true. So ddt of the integral of U dot V plus the integral on omega of U dot grad U times V plus the dual pairing AUV X prime X is 0 for every V in X. Okay. Theorem. Again, not surprisingly, let U not be in H, then there exists a unique weak solution with this initial data. And this theorem was sort of present in Jim's thesis from 2006, but as I said, there were some issues with the proofs. Furthermore, more interestingly, the following energy identities hold true, all of them. 1. So this comes from taking U equals V in the expression for the weak solution, the identity for the weak solution. So ddt of the L2 norm squared of U plus 4 times viscosity times SU L2 squared is minus twice viscosity nu integral on the boundary of alpha U squared. ddt of L2 norm squared plus twice times the curl times omega L2 squared is twice nu times 2 kappa minus alpha U of t squared. So this is the norm of U of t squared, the Euclidean norm, integrated on the boundary. And 3, ddt of U of t L2 squared plus 2 nu times the L2 norm squared of the gradient is 2 nu times the integral of kappa minus alpha U of t squared. Okay. So as a result of these three energy equalities or energy identities, what we'll see then is that the exponential decay of U comes down to Poincare inequalities for each of these terms here. So if I can estimate U L2 squared by SU L2 squared or by omega L2 squared or by the gradient of U L2 squared, then assuming sign conditions on these coefficients, alpha, 2 kappa minus alpha, and kappa minus alpha, I'm done, at least for the L2 norm squared, decay of the L2 norm of U. So let's discuss Poincare type inequalities. First, we start by noticing that for any vector field in H, because of the divergence-free condition, each of the components of H has average 0. Therefore, you can use a standard Poincare inequality for mean 0 functions to show that the L2 norm of U is bounded by a constant times the gradient, the L2 norm of its gradient, for any U and X. Okay, now, if you have a vector field in X and omega is simply connected, then of course there's no harmonic part of U. There's no harmonic vector fields. The space of harmonic vector fields is trivial. Therefore, U is exactly equal to its Biot-Savart law for omega. And then by the Calderon-Zygmunt inequality, the gradient of U and L2 squared is going to be the gradient of the grad perp of the Laplacian inverse of omega and L2 squared. In other words, a 0-order differential operator applied to omega, and that's obviously bounded by C times the L2 norm squared of omega. Therefore, in this case, you can show that U, L2, is bounded by C times omega L2, using the first Poincare inequality. Okay. Furthermore, now we have this intriguing proposition. If omega, with the exception of the disk or the annulus, and it doesn't matter where the center is, then the L2 norm of U can be bounded by the L2 norm of the symmetric stress matrix SU for any U in H1 tangent to the boundary div free. So there's some constant C such that the L2 norm of U is bounded by C times LCU L2. Okay, here's a remark. This inequality cannot hold in a disk or an annulus. This does not hold. Indeed, we have the following lemma. If U is an H1 and SU equals 0, then U is an affine function. And because this is a symmetric tensor, a symmetric matrix, then it has to be of the form a constant vector plus a multiple of x perp. So x perp is minus x2, x1. Okay. Now, this is pretty easy to prove. And therefore, if omega is neither a disk or an annulus, and it belongs to H1, then both of these constants, A and B, have to be equal to 0. And that's simply because A plus Bx perp cannot be tangent to a boundary unless the boundary is circular. Okay. On the other hand, if omega is a disk or an annulus, and U is a function which satisfies the Navier boundary conditions, then unless alpha is equal to 0, then A equals B equals 0. However, if alpha equals to 0, then there exists non-zero constants A and B such that SU equals 0. So we would have SU equals 0 here without U being 0 here. So this inequality cannot hold in general for all U's and X. There are U's and X for which this doesn't hold, obviously. Okay. Okay. Now, decay of U in L2 follows directly from the energy identities plus the Poincare inequalities under each of the assumptions. And notice that this doesn't need U to be in W. This is enough. It's enough to have a weak solution, and you already have exponential decay. Indeed, from the energy identity, dTu L2 squared plus 4 nu SU L2 squared is minus 2 nu alpha. If omega is not a disk or an annulus, then you know you have this Poincare inequality. U is bounded by SU L2. So as long as you can throw away your right-hand side, you get the necessary decay. Okay, so in that way you can throw it away as long as alpha is greater or equal to 0. Using this other energy identity, whenever U is bounded by C times omega L2, you also can throw this right-hand side away if you assume that alpha is greater or equal to 2 kappa. So this is going to be a negative term. Okay, and this and you have this Poincare inequality for simply connected domains. And finally, you have a general Poincare inequality valid for any domain, okay, omega. And you get the desired decay if you assume that kappa is less than or equal to alpha everywhere on the boundary. So this is pretty simple. Now, it's the decay of U in L infinity and of omega in L2 and L infinity that you need a strong solution. Here's where you need to have a strong solution, because you need to make use of the pointwise traces of the first derivatives on the boundary. So first of all, theorem. If U naught is in W and U is a weak solution with initial data U naught, then actually U is better. It's L2 in time into W, and dTu is L infinity into H and L2 into X, not only X prime, but actually X. So dTu is L2 into H1. Moreover, you can find a pressure, which is an L2 of time into H1. Okay. All right, now in 1998, Clopot, Michaelich, and Robert showed that the Navier boundary conditions are equivalent. This is actually if and only if to a boundary condition for the vorticity. So the vorticity at the boundary is 2 kappa minus alpha U dot tau at the boundary, the tangential component of the velocity, which is the only component of velocity at the boundary. Okay, and what this does is this will give us a local boundary condition for the viscous vorticity equation. And we're going to use this to get the L2 decay for omega and the L infinity decay for U and omega. Okay, so this is based on vorticity maximum principal estimates. As I said, the Navier boundary condition then gives you a local boundary condition for the viscous vorticity equation. So the viscous vorticity equation is obtained, as we all know, by taking the curl of the NeverStokes equation. So you get dt omega plus u grad omega is nu Laplacian of omega. U is given in terms of the Biot-Savart law for omega plus a harmonic part. Initially, omega is omega naught, which is going to be the curl of u naught. And on the boundary, omega is 2 kappa minus alpha u dot tau. So we actually have a boundary condition for the vorticity, which is what we're missing in the no-slip case. Okay, so we use comparison principles to get control of omega L infinity in time into LP if P is greater than 2. And this is an extension of work that was done by Milton Lopes, Gabriela Planas, and myself back in 2005, I think it was published. So we have the following proposition: let U be a strong solution of 2D NeverStokes with Navier boundary conditions. Omega is the curl of U. Then for any P greater than 2, there exists a constant such that the LP norm, L infinity in time, is bounded by the initial LP norm plus the initial L2 norm of the velocity. And furthermore, the L infinity norm in time into L2 is exponentially decaying, plus a constant times this object lambda, which I'm going to explain what it is in a second. Okay, so this was not present in the paper with Milton and Gabriela, and this was done only in the case. This estimate here had been done only in the case of simply connected domains. Okay, and this was included in Jim Kelleher's thesis from 2006, I think, with the exception of the second estimate. I'm not sure though. Here's an outline of the proof because it's kind of cute. So lambda is the L infinity norm of 2 kappa minus alpha times the tangential velocity on the boundary. So it's L infinity in time and on the boundary. So first we take omega tilde, a solution of the following parabolic equation: dt omega tilde plus u grad omega tilde is nu Laplacian omega tilde, where u is the velocity from the NeverStokes solution. So it's given. And omega tilde at time t equals 0 is the absolute value of omega naught. And on the boundary, it's equal to this constant lambda, which is a constant in time and in space. Then, since omega is, the absolute value of omega is less than or equal to omega tilde initially and on the boundary, because of the Navier boundary condition, then we get that everywhere on omega, on capital omega, absolute value of the vorticity is bounded by omega tilde. Then we take omega hat, which is the difference of omega tilde and this constant lambda. Turns out that omega hat satisfies the same kind of parabolic equation with the same velocity field u, but with zero boundary conditions, Dirichlet boundary conditions. And the initial data is absolute value omega naught minus lambda. So a simple energy method gives you LP inequalities for gives you the following estimate for ddt of the LP norm to the pth power of omega hat. Okay, so since this quantity is always negative, you trivially get that omega hat in LP is less than or equal to omega in the initial omega hat. Okay, and the initial omega hat is bounded by the LP norm of omega naught plus lambda. And since omega hat is omega tilde minus lambda, and omega tilde is greater or equal to omega to absolute value of omega, you finally end up with the L infinity norm of omega into LP in time into LP is bounded by the initial LP norm of omega naught plus a constant times lambda. If you take P equal 2, then what you get on your right hand side is minus twice nu, the integral of the gradient of omega hat squared. And you can then use the Poisson inequality to bound this by the integral by minus twice nu, the integral of omega hat squared. And since on your left hand side you'll have ddt of the L2 norm squared, you easily get that the L2 norm squared of omega hat is exponentially decaying therefore, the L2 norm of omega times t is bounded by some constant times this exponentially decaying object here, plus constant times lambda. So in order to conclude, we just have to estimate lambda. So lambda is bounded by the L infinity norm of 2 kappa minus alpha times the L infinity norm of the velocity on the boundary. Now, from the Sobolev embedding, if omega is LP, then U is W1P, and P is greater than 2 means that U is a continuous function. Okay, and this is in the interior. Therefore, the L infinity norm of U on the boundary is bounded by the C0 norm on all of omega times time. Okay, but you can forget time at this point. Okay, and therefore, what we've just shown is that W1P is contained in C0, and C0 is clearly contained in L2. So you can interpolate between L2 and W1P and use the harmonic part to find that the L infinity norm of U at time t on the boundary is bounded by the L2 norm of U in the interior to some power theta times omega time t LP plus U at time t L2 to some power 1 minus theta. So this is just Sobolev embedding plus interpolation, and this term here comes from the harmonic part. So you conclude the theorem with the Young's inequality. So this is kind of a bootstrap. Okay, so the proposition implies exponential decay of U in L infinity from decay in L2. Okay, because now we already know that UL2 here and here decays exponentially. We've already proved that for weak solutions. So this gives you the exponential decay of the L infinity norm of U on the boundary, which will then give you the exponential decay of U in the interior. Because actually this estimate here could be made at just as well in the interior. Okay. Okay. But notice that we do need U to be better, to be in W. U in H1 is not enough because we did use the actual boundary condition omega is 2 kappa minus alpha times U dot ta to deduce this. You also get exponential decay of omega in L2 because we already found this estimate here. And so all we need is to estimate lambda and show that lambda decays exponentially. And the way to do this is to restart time at some t not positive, and then use the exponential decay of U in L infinity to get the exponential decay of lambda. Okay, so the key step to get the exponential decay in L infinity for omega is going to be a Nash iteration argument. Okay, so we prove that omega hat at time t bounded in L infinity is bounded by 1 over square root of nu t times omega hat at some earlier time, in this case t over 2, on L2 of omega. Okay, so here's a Nash method. So we start from this basic energy estimate. We use interpolation and the Lagrange inequality in 2D to show that your right-hand side is bounded actually by the LP norm of omega hat to the 2p times the LP over 2 norm of omega hat to the power p. Of course, this is bounded by the initial LP over 2 to the pth norm of omega hat. Okay. And therefore, if you write p equals to 2q, you have the following estimate. ddt of the L2q norm of omega hat to the power 2q is bounded by nu times the L2q norm of omega hat to the power 4q, that's the 2p, over the LQ norm to the 2q of omega hat at some time t naught. Okay, so finally, we integrate this. We use just Grunwald's inequality. We integrate this, and we get this estimate for the L2q norm of omega hat to the power 2q. So, and this is true for any t greater or equal to greater than strictly t naught. Now we can iterate this estimate starting from q equals 2 because we have some notion of what happens with the L2 norm of omega hat. Okay, this iteration, so as you start with q equals 2, this gives you an estimate in L4, then you plug the estimate in L4, and this gives you an estimate in L8, and so on and so forth. And this iteration converges eventually to the L infinity norm of omega hat. So finally, you get this estimate. This is known as the Nash method. The infinity norm is bounded by a constant, a universal constant, over nu t minus t hat to the 1/2 times the L2 norm of omega hat at time t naught. And you just take t naught equals to t over 2. Done. Okay, so from the lemma, you have exponential decay of omega in L infinity because you have exponential decay of L2. Okay, now omega is bounded by omega hat plus lambda. You already proved that lambda has exponential decay, therefore done. Okay, so I'm going to wrap up with some comments and conclusions, a couple of comments and conclusions. First of all, note that the disk and the annulus are somehow special. So we can find alpha, namely alpha equals 0, okay, and solutions of 2D NeverStokes with never boundary conditions that do not decay. So alpha equals 0, and if you take without loss of generality the center of either the disk or the annulus to be the origin, then U equals X perp is a steady solution of both 2D NeverStokes with never boundary conditions and Euler. Okay, that's because the Laplacian of X perp is 0. Okay. So this is a steady solution, therefore it does not decay. Okay. And if your omega is not centered at the origin, then it's going to be some constant plus X perp. Okay, now the other observation is that there's a paper by J.G. Butcher from 1876 where he argues that the solution of the NeverStokes equations with never boundary conditions with some friction alpha, and here he's thinking of alpha positive, is kind of akin to the solution of the NeverStokes equations with low slip if the boundary were pushed to a distance 1 over alpha beyond the actual boundary. So, and 1 over alpha is supposed to be the slip length. Okay, now of course this only makes sense as long as 1 over alpha is much so smaller than the size of the domain because of the asymptotics. Okay, now 1 over the curvature is not an actual size of domain, but it could be viewed as a proxy for the size of the domain. And in case of a disk or the annulus, basically this is exact. So based on Butcher's analysis, you should have what you should expect 1 over alpha much smaller than 1 over kappa, or in other words, alpha greater than or equal to kappa. And this sort of arises naturally. Weird. Okay. And sorry for the briefness, but that is all I have to say for today. Thank you. Obrigada.
Thank you very much, Helena. Let's thank Helena for this great talk. So now if you have questions, you can unmute yourself or you can write your question on the chat. So are there any questions or comments?
I have a question.
Yes.
Hello?
Yes.
Yeah. So I'm a physicist, so maybe this is naive, but either I misunderstood something, or if you have a negative viscosity, if you have a viscosity more or less than 0, so basically any perturbation will blow up, you still have solutions which decay exponentially. For
yeah, no, we're not looking at negative viscosity. We're considering possibly negative friction. Is that what you mean?
Yeah.
Ah.
Yeah.
Yes. Mm-hmm. Yes, that is correct.
Friction, by friction you mean with the boundary condition, the interaction between the fluid.
I mean alpha.
Okay, I see. So this is different from viscosity, of course.
Yes.
Is there this is a little bit counterintuitive.
Correct.
Yeah.
Correct.
Is there sort of a...
If you have holes, then you necessarily have negative curvature.
True.
Okay, so what we're saying is that on the holes, right, you could have negative alpha, sort of accompanying the curvature.
Okay. I mean, negative alpha basically means the fluid is driven to spin faster and faster around the holes.
Yeah.
That's what it means. And yet, velocity decays exponentially in long time scales.
Yes. I know it's weird. It's counterintuitive.
I mean, yeah. Okay. I mean, it's a toy model. And I mean, it's not really a toy model because you could mock up in an experiment with a two flow, you could mock up negative friction by a driving force, right?
Yeah.
And then that
I don't know how that would work out because we didn't include force in our analysis.
Okay. Okay, thanks. Thanks.
Okay, are there any other questions or comments? Okay, so if not, let's thank you, Helena, again. Thank you very much.
Thank you.
So now we'll have